Hi, my name is Intak Hwang, and I'm a PhD student at Seoul National University. And I'm studying lattice-based cryptography for most of my time. So I'll start my presentation, and as I said earlier, I'll just disable my video because it'll freeze anyway. Okay. So is it showing right now? Okay.
Yep.
Yep. Okay. I'll just start. So hi everyone. As I said earlier, my name is Intak Hwang, and today I'm gonna present our latest work, Practical TFHE Ciphertext Sanitization for Oblivious Circuit Evaluation. So for those who have attended this year's FH.org at Sophia, this work was actually presented as a poster under the title Practical Circuit Privacy / Sanitization for TFHE. But since then, we revised this paper quite heavily, and this is our new title now. So actually in ePrint, our paper is not yet updated, so we'll try to update it as soon as possible, and I apologize for that. But anyways, yeah, let's begin. Okay, so first, I want to start this presentation by introducing a very natural protocol called Oblivious Circuit Evaluation from Homomorphic Encryption. So this protocol is quite simple. Assume there are two parties. The left party holds the input X, and we'll call this party a client. And the right party holds some input C, or a circuit C, rather, and we'll call this party just server. So after this protocol, the client learns the evaluated value, Z, and the server learns nothing. So now we can immediately think of a way to realize this using homomorphic encryption. First, the client just samples some keys and encrypts its input using homomorphic encryption. And then it sends the evaluation key and the ciphertext to the server. And the server evaluates the circuit over the ciphertext homomorphically and obtains output ciphertext CT_out and sends that back to the client. And the client simply decrypts this ciphertext and obtains C. Pretty simple, right? So the fascinating thing about HE is that via the NDCP security of homomorphic encryption, the server does not know anything about the input X. Basically, it's because it's just encrypted under some encryption scheme. But the question I want to pose in this presentation is actually quite interesting. It is that, is it true the other way around? So in other words, can the client know something about the server's circuit C? So one might think this question is unnatural, but actually this question very naturally arises in multiple 2PC scenarios from HE. For instance, consider some sort of private set intersection protocol. In this protocol, two parties jointly compute some intersection between the sets, and the server may not want to disclose the information about the set to the client. Or in the private information retrieval protocol, the server may not want to disclose any information about the database. Or in the private privacy-preserving machine learning protocol, the model, and so on and so on. But in this talk, I'll focus on much more simple protocol called Oblivious Linear Evaluation, or OLE for short. This is actually a very important building block for many cryptographic protocols. So it's quite simple. Party 1 holds an input M, and party 2 holds a linear circuit AX plus B. So after the protocol, the client or the party 1 learns Z equals AM plus B mod P. So the construction is simple. Again, we encrypt the input M and sends it to the server. Server evaluates A times CT plus delta B and returns the ciphertext to the client, and it decrypts it. So the question is, can the client or party 1 learn any information about A and B? Note that generally it should not, because in these types of OLE protocol, the inputs M, A, and B is actually random one-time values, so we cannot just deduce A and B from V. However, in this case, the party 1 can actually learn some information about A and B. We can see this by just carefully looking at the ciphertext CT_out. The ciphertext CT_out looks like this. And here, the party 1 actually knows two values, U and A times U, from the masking or the second part of the ciphertext. So it can just simply divide these two values and learn A, and thus B. So the answer to this question, is it true the other way around, is actually no. So to solve this problem, a new security notion called circuit privacy was introduced. As a matter of fact, Gentry himself coined this term. Apparently, this issue was from the get-go. But anyways, we say an HE scheme is circuit private when no information about the evaluated circuit remains in the output ciphertext. So by definition, an Oblivious circuit evaluation protocol over a circuit private HE scheme is secure, at least in the semi-honest model. There's also a slightly stronger notion called sanitization, which we will focus on this talk. Roughly speaking, a sanitization algorithm strips the information from the ciphertext, except from the message, of course. Or put it in another way, any two ciphertexts with the same message should be indistinguishable after sanitization. So we can easily see that sanitization implies circuit privacy because we can just simply sanitize the output ciphertext after evaluation and achieve circuit privacy. Okay, before we dive into more details, we'll stop here a little bit and think about why achieving these advanced security notion is actually difficult. Okay, one might think that maybe we can just simply add encryption of 0 before returning the output ciphertext to the client. Then the mask value of the ciphertext will be become some unknown value, so the aforementioned attack won't work. So this is actually true, but the problem is that ciphertext contains much more information than just the mask. More importantly, it contains the noise, so we can actually apply the exact same attack with the noise value, because the noise value will contain the information about A. So this won't work. Okay, if the noise contains this value, maybe we can just bootstrap the ciphertext and just remove the noise. Yeah, this actually makes sense, and these two questions are like the building blocks of the more advanced construction we'll talk about later. But simple bootstrapping won't work either. This is because while bootstrapping can remove the existing noise, during the bootstrapping, a new noise is introduced, and that new noise may still depend on the input ciphertext. So in a simulation-based security standpoint, the new noise introduced won't be simulatable, hence we won't be able to make a secure 2PC from this. Yeah, so these types of approach won't work, and we need another approaches to achieve circuit privacy or sanitization. Okay, so from now, I'll actually talk about how we can actually achieve these notions. The first and the most widespread approach to achieve sanitization is called noise floating. Essentially, this is based on our previous idea of adding a public key encryption of 0. This also adds an encryption of 0, but with a very, very large noise, almost exponentially larger noise than the existing noise. So basically, this new noise statistically drowns out the existing noise, hence just removing any information from it. So this is quite simple and very fast and easy to understand. But the problem is that we have to account for this added noise. And as a result, we'll have lambda bit overhead with the parameters. So this is especially crucial for schemes like TFHE because it operates in small parameters or type parameters. Okay, for example, in typical TFHE parameters, the ciphertext modulus is around 64 bits, right? However, when you take lambda to 128, as we usually do, the amount we have to add already exceeds the ciphertext modulus. So we cannot do anything about it, really. Okay, so to somehow solve this problem, another approach called silk spin repeat sanitization was proposed. The key idea of this is that instead of doing a large noise flooding at once, it splits the noise and do flooding multiple times. To be specific, it first does a moderate size of noise flooding, and then it bootstraps the ciphertext to reduce the noise. And by sufficiently repeating this cycle, the existing noise will be statistically flooded at some point. So this approach especially suits PO or TFHE style schemes because they have small parameters and very fast bootstrapping. However, obviously, this will incur some overhead to the performance, or concretely, to achieve sufficient sanitization, we'll have to repeat this cycle O lambda times. So it'll be a little lambda times slower than normal bootstrapping. And concretely speaking, we have to repeat this cycle around 10 times. So it'll be 10 times slower than normal bootstrapping. So these two approaches are quite generic approaches that is applicable to any FHE schemes. From now on, we'll talk about TFHE-specific sanitizations. Before that, we'll just briefly review the TFHE bootstrapping process. So usually TFHE bootstrapping consists of 3 phases. In the first step, key switch, we reduce the dimension of the input LWE ciphertext. In the next step, called blind rotation, we homomorphically decrypt the ciphertext in the exponent, outputting a RW ciphertext with rotated lookup table. So an interesting property here is that we can actually compute an arbitrary lookup table with it, but that will not be important in our talk, so we'll just ignore it for that for a while. In the final step, sample extract, we extract the constant term of the RW ciphertext back to LW ciphertext, finishing the bootstrapping. Okay, so in this paradigm, prior 2 works, BI22 and CLU22, randomize the blind rotation step to achieve sanitization. Essentially, they used randomized external products, which replaces a deterministic Gaussian gadget decomposition to a randomized Gaussian gadget decomposition. Then, by some convolution property of Gaussian distribution, you can remove the information of input ciphertext during blind rotation. So this does seem quite well. So this solves the problems of aforementioned approaches. So it only requires a single bootstrapping, and its parameters overhead is not that large. But the problem is that, in concretely speaking, it often performs worse than silk speed repeat sanitization because it requires a very large number of Gaussian samples. And especially discrete Gaussian sampling is notoriously hard to sample. So is there a way that we can do better? Can we reduce this randomization step? This was a question that we aimed for in this work. Okay, so now we'll talk about our approach. So our approach essentially works in 2 steps. First, we take the original blind rotation. And then, first, we add a mask re-randomization step in front of the blind rotation. So what mask re-randomization does is that we remove the information of A by essentially re-randomizing it back to uniformly random value. So using mask re-randomization, the information about A is removed, but the information about B still remains. So to solve this, we can just simply ignore B. And now the output ciphertext is simulatable only with A, which is a uniformly random value now. But the obvious problem here is that correctness will be wrong. To finally solve this problem, we can multiply this monomial, x to the rounded 2n over qb, at the end of the blind rotation. But blindly multiplying this will, of course, incur a dependency on b again. So we adapt a Oblivious linear evaluation technique from prior work. Basically, this is oblivious in a sense that the output ciphertext can be simulated without the knowledge of the plaintext, or a monomial in this case, being multiplied. So with these 2 steps, the information about the input ciphertext, B and A, can be removed, finally achieving sanitization. Okay, so let's talk about a little bit of technical details. First, for mask randomization, we essentially add a carefully crafted public key inference of 0, which has a uniform mask key. So recall that usually a public key inference of 0 is made by computing R times PK plus E0, E1. Here, after computation, this CTRAN has masking of the form UR plus E1 with an error or noise of E hat R plus SE1 plus E0. So the masking UR plus E1 is actually a RW sample with a key R and noise E1 with a linear hint E hat R plus SE1 plus E0. Actually, these types of linear leakages are very common in LW-based constructions. And it is actually well known that even with this linear leakage, an RW sample is still indistinguishable from uniformly random value under some mild conditions. So using that, we can essentially show that the masking of CTRAN is indistinguishable from uniform value. And since Since uniformly random, if we can just add any constant or independently random variable to a uniformly random value, it still becomes uniformly random. So what we have here is that we can just simply add ctrand to any ciphertext and re-randomize the masking back to uniform. For the oblivious or randomized linear evaluation, we borrow a trick from DCKKS plus 24. So recall that usually we just multiply mu to the ciphertext to achieve linear evaluation. But here we sample a Gaussian random value called mu hat, which is a Gaussian value from the cosine mu plus TCI. And also we sample a smoothing Gaussian value and then compute mu hat times CT plus E hat comma 0. So this way the coordinates obviously holds because the plaintext arithmetic is done modulo T. However, the noise of CT out is now hand mu E plus hat E, which actually follow this Gaussian value. So this looks quite intimidating, but the key idea here is that this Gaussian value is actually independent from mu. So you actually just remove the information about mu in the output ciphertext CT out. Of course, there are some information about mu left in the masking of CT out, but we can just remove it using ctrand we just discussed earlier. Okay, so with these two steps in mind, let us rewrite our sanitization algorithm. So as we discussed earlier, our sanitization as mask re-randomization and randomized linear evaluation at the beginning, at the end of the blind rotation step. So here, I colored some arrows in red. So the red arrows means that there are some components that depends on the input ciphertext. So essentially, this is not simulatable. After mask re-randomization step, the masking becomes uniform. So the ciphertext up until the randomized linear evaluation step is not simulatable. This is because the simulator now can just simply run the same algorithms with a uniformly random vector from ZQN. Okay, now after the randomized linear evaluation step, we can simulate the output ciphertext by using the property of randomized linear evaluation that we talked earlier. So basically, the output ciphertext of randomized linear evaluation is independent from the plaintext being multiplied, this monomial in this case. So the information about B is removed here in this step. So basically, we can achieve sanitization by simply adding these two steps. Okay, so finally, we'll compare our work to the previous works. The noise floating approach was simple and fast, but it needed an exponential overhead in parameters. The silk-spin repeat approach solves this problem and only needs a small parameter overhead, but it required consecutive bootstrappings. Prior works that focuses on TFHE sanitization, BI22 and CLOSE22, only needed a single bootstrapping and a minimal parameter overhead, but in practice it was slow because it needed an excessive randomization. Our sanitization solves all of these mentioned problems. We only need a single bootstrapping. We incur minimal parameter overhead. We only require minimal re-randomization. And another thing I want to emphasize here is that we use all of this line rotation and all other components of bootstrapping as a black box manner. This means that we can readily apply our sanitization to any other AP style scheme, such as Vue or LMT CDY. And also, we can just directly apply any TFHE advancements of TFHE bootstrapping in performance. So basically, we can just use those works directly as long as they don't harm the API of the blind rotation. Okay, our sanitation is readily implemented in the TFHE Go library, which is a library that I've been working on quite a while. So it implements the TFHE and multi-key TFHE scheme in Go. And as we look at the experimental results, we compare the sanitization with the bootstrapping with the same parameters. So the prior works actually incurred a huge overhead compared to the base bootstrapping algorithms. But in our work, the difference is less than 1 millisecond, or like 2 or 3%. So basically, the overhead is almost negligible. And we can sanitize a ciphertext in the same rate as we just bootstrap it. And we can use this optimization that recall that the sanitation only happens at the end of the evaluated circuit, right? So basically, we can merge this sanitation step with the last evaluation of, or the last bootstrapping during the circuit. So if we consider that approach, then basically the overhead is just negligible. Okay, so this was the first part of our presentation. So let's go back to the Oblivious circuit evaluation for Reishi. So using sanitization, we can achieve the secure Oblivious circuit evaluation in the semi-honest form. So naturally, we can ask, how about in a malicious model? So what if client is malicious? Then the client may be able to like alter the keys and the ciphertext in a way that it can get more information about this server's circuit. So what we do is basically what everybody else does. We just add zero knowledge proofs, and we're just done. But actually, in practice, this is much harder than it sounds. To handle malicious clients, as we said earlier, we need zero knowledge proof for keys and ciphertexts. So basically, we need to prove the well-formedness or validity of blind rotation keys, key fetching keys, and public key and the ciphertext. These include relationships over power of two cyclotomic rings and some range checks over the message bound or the error bound. To prove this, we use Buckler, which is our work. We use Buckler because it has sublinear or square root and proof size. It is actually zero knowledge, unlike other proof systems. And it is also optimized for RLW relations. Okay, so even though this work does not really focus on these proof systems, we'll give an overview here anyways, because it'll be easier to understand our work. So Buckler supports two types of checks, following the idea of univariate PIOP-based snarks, such as Aura and Marlin. So these checks consist of two. First one is a row check, which checks the element-wise addition and multiplication of vectors over ZQ. And the second one is linear check, which checks the linear transformation between vectors over ZQ. It turns out that basically all RW relations can be proved with only these two types of checks, row check and lin check. So how we'll give an example of proof of public key. So to prove a public key, we need to prove these relationships. B equals minus AS plus E mod Q, and S is binary key, and E is some ternary error. So actually, it may be a larger bound, but here for simplicity, we consider only a ternary error. This can be essentially proved by the following. First, we do a row check on entity vectors of these values. So basically, the relation B equals minus AS plus E is equivalent to B entity vector equals minus A entity vector, Hadamard product S entity vector plus E entity vector. Over ZQ, of course. And for the binarity of S, we check that S multiplied by S minus 1 is 0. And similarly for the error, we check that E minus 1 multiplied by E plus 1 is 0. These row checks essentially consist of range proofs. So basically, these checks are checking that E and S is inside a certain range. Finally, we use a consistency proof because here we have the entity vector of E and the coefficient vector of E. So we have to prove that these two vectors are actually consistent. And we use the fact that entity transformation is actually a linear transformation. So using lin check, we can prove that S entity vector is actually an entity transformation of S, and similar with E entity vectors. Okay, finally, we will talk about some optimization tidbits. So first, the obvious problem was that there were too many constraints. The TFHE evaluation key itself already consists of like hundreds of megabytes or even gigabytes, which takes too long to prove. To solve this problem, we essentially compress the public keys as much as possible. For example, blind rotation keys can be compressed essentially to a linear rotation key and a godless keys. Similarly, key fetching keys can be compressed to a single RGSW ciphertext since it consists of many GSW ciphertext. So using these techniques, we need a single relinearization key, log n Galois key, and a single Aristotelian ciphertext, which in total have OD and log n Aristotelian ciphertext, where D is a dimension of gadget and N is a ring dimension. Another problem we have that actually typical parameters for TFHE does not guarantee enough soundness for proof system. The main reason is that due to Schwar's lemma, the soundness depends on the size of the modulus, or more formally, the inverse of the soundness modulus. However, in typical TFH parameters, Q is only 64 bits. So this means that the soundness error will be 2 to the minus 64, which is not sufficient because we usually target for 2 to the minus 128. So to solve this problem, we actually use a very clever technique that actually we generate the keys in a larger modulus. So we generate the keys in 128-bit modulus. And during decompression, we modulus switch to a smaller modulus, to the 64-bit modulus. This essentially gives us two benefits. First, it guarantees sufficient soundness, as we can prove the relationship over a larger modulus. And second, we can suppress the decompression noise. So during decompression, we have to do very many key switchings, which incurs some very large noise. But we essentially modulus switch at 64 bits, so those noise is suppressed to the rounding error. Okay, there are actually many other optimizations that we did for our proof system, but due to lack of time, we just introduced only two of the main optimization. And if you have any more questions, then you may ask in the Q&A section, or you can just look at our paper. Okay, so the implementation of our proof system can be done using our Ringo Snark library, which is another library that I'm currently working on. It actually offers a Gnark-like automatic compilation of proof system. Okay, so a single thread prover runs approximately 196 seconds, so approximately 3 minutes. But using 16 threads, we can reduce that to like about 20 seconds. And also the verifier runs about 24 seconds. So you may say that this is in a practical range. And also, I'll say that further optimizations are even possible. For example, we can use the noise-proof optimization technique from Pelta. Essentially, what this does is that instead of proving a very large noise, so instead of doing a range check for a very large noise, it proves that the noise is essentially generated by yet another Artlev ciphertext. So then the witness that we have to prove is very small. Also, we can only use 2 Galois keys instead of log n Galois keys, because essentially you can just do any rotations using only 2 Galois keys, which is Galois keys for 5 and -1 automorphism. So using these optimization techniques, we believe that our expected proof of performance will be around 1 minute or 2 minutes, so around 100 seconds in a single thread. So in multi-thread, it may be much smaller. So actually, before uploading to ePrint, we're planning to apply these optimizations. So hopefully, we have much more better performance when this paper is actually uploaded to ePrint. Okay, I'll end this presentation with some open questions. First, you may notice that there are some missing parts in this presentation. Most notably, we missed the scenario when the server is malicious. So we only consider the case where the client and the server is semi-honest, or the client is malicious, but not when the server is malicious. To achieve this, we will need a verifiable FHE, but not just verifiability, but also zero-knowledge verifiable FHE, because here we are also trying to hide the circuit itself. As far as I know, there's only one work that does this, which was accepted in this year's SMP, but the target of that paper was more closer to CKKS or BSV BGV, not TFHE. In case of TFHE, as long as I know, there's actually no work that does this in the practical realm. So I'd say it's still very far from practice. It'll be very interesting if you can do that in practical time. Another good question would be about other schemes. So can you achieve efficient circuit privacy for other schemes? So it seems that our approach won't work for other schemes because our approach very heavily depends on the linearity of bootstrapping, whereas in other schemes, they don't have such good property. However, our lab recently focused on these line of work quite heavily. So in case of BFP, we showed that by relaxing circuit privacy and define a new security notion called ciphertext simulatability, we can achieve very efficient 2PC. Basically, the idea of ciphertext simulatability is that we just leak the entire description of the circuit and only hide the inputs of the server. So in case of TFHE, these notions, these relaxations have not so much effect, but in BFV it does because it consists of much more different and various kinds of operation. So actually, Yongsu did talk about this work in this year's TFH.org. So if you're interested in this line of work, please check it out. And a more difficult question would be regarding CKKS. In case of CKKS, the noise and the message are intertwined, so it is hard to even define what sanitization or circuit privacy means in that context. If we try to define it, then it falls into either too trivial definition or a definition that basically we cannot really achieve. So our lab recently published two works focused on TKKS. In the first work, we showed that instead of doing the server doing the noise flooding, if we do some sort of distributed noise flooding that involves both clients and server, then we may be able to build a UPC from CKKS. Or the other work focused on a different kind of security notion called differential privacy, and show that basically we can use CKKS in context of DP protocols similar to universal compatibility framework. But I'd say that these two works are not really satisfactory as our work on TFHE, and further work would be really nice that advances this line of work. Yeah, so that's about all, and thank you for listening to my talk. Here are some links to the paper and some implementation that I talked about in this paper. And yeah, I'd be happy to take any questions. Thank you.